style as we did for the various elements. I start here with the big picture. That's the evolution of the Earth. We have solar nebula accretion, which means you form planetisms are formed, including the Earth. And then comes the core mantle fractionation, which is the most important chemical event in the history of the Earth. And all this happens within a very short time, so at 4.55 billion years. And then we have a core, metallic core, and a silicate mantle. The mass relation is about 1 to 2. So this core mantle fractionation is the first and most important process. And in the following, we have fractionation in between different silicate reservoirs. Because we have the mantle crust fractionation, which means it's the formation of the continental crust. And then for the last 2 billion years maybe, we have dominantly intracrustal fractionation, which means within the crust there is a fractionation going on, and the process which is done by this fractionation is granitic magmatism. And related to these different steps here, different reservoirs, I have listed here a number of elements, including tin, tantalum, and tungsten. And we start out with the C1 chondrites. And in the C1 chondrites, we have about 1.7 ppm tin. That's the starting material for the Earth. 1.7. And then the bulk Earth only has about 0.4 ppm. The reason is that this kind of fractionation is called volatile fractionation or volatile refractory fractionation. Tin is a volatile element, a volatile metal. And during the accretion process, the volatile components are spilled out into the outer part of the solar system. The inner part of the solar system with the Earth and Venus and Jupiter. No, Jupiter not. Earth, Venus, Mercury. These elements, the inner part of the solar system, they have concentrated refractory components. They lost much of their volatile components. And tin is one of these volatile components. That's different, for instance, from tantalum. Tantalum is highly refractory. So the concentration in the chondrites is about 14 ppb. And then in the bulk Earth, we have 23 ppb. So tantalum is slightly enriched because of this refractory volatile fractionation. That many volatile components are lost of the paleo-Earth. This is why tantalum is slightly enriched in the bulk Earth. And tungsten, for instance, tungsten is the same. Tungsten is also highly refractory material, is also slightly enriched in the bulk Earth compared to the starting material, which is a solar nebula, which has a chondritic composition. Yeah, well, from the bulk Earth now, we go to the primitive mantle here in this table. And in between bulk Earth and primitive mantle is the core mantle fractionation. This is segregation of the metallic iron core. This has dramatic consequences. Or let's say, for some elements has dramatic consequences, for gold, for instance. Yeah, I put gold here. So in the bulk Earth, we have about 260 ppb gold. And in the primitive mantle, there's just 1 ppb left. The reason is that most gold is lost to the core. We cannot sample the core, but we can sample iron meteorites which fall on Earth free of charge. And they are enriched in gold and other siderophile elements as it should be. So from the bulk earth we go to the primitive mantle, and there we see that tin is slightly depleted because tin is slightly siderophile. So during this core mantle fractionation, the larger part of tin goes into the core. And only a smaller part is left for the silicate material. So we have in the primitive mantle about 130 ppb tin. Okay. And the tantalum is highly lithophile. This means no tantalum doesn't go into the metallic core. It is enriched in the primitive mantle silicate material. And then we have an enrichment factor of about 1.5 as it should be. Because 1.5 is a mass ratio between the core and the primitive mantle. So, and then from the mantle we come to the continental crust. You know, the continental crust is formed by melting of the mantle. And this process by partial melting, not bulk melting. It's a partial melting, very small degree melting, which happens mostly at mid-ocean ridges. 90% of all volcanism today is at the mid-ocean ridges. Also, we do not see it because it's underwater usually. Only 10% of volcanism happens on the continent. So, and during this process of the basalts are formed. Basalt is a partial melt from the mantle. Only a few percent of melting. And this is why the basalt then, which is produced here from the primitive mantle, and which finally, by recycling, ends up as a continental crust, is enriched. White continental crust has about 2 ppm. And in between here, you see this is a factor of 10. This factor derives from this more or less a degree of partial melting. On partial melting, tin goes into the partial melt. And if you have 10% partial melting, then tin could be enriched by 10 times. If it goes fully into the partial melt. But nobody is perfect. Actually, in geochemistry, we also talk about perfectly incompatible, for instance. This is just a model. In nature, there is no perfectly incompatible element, of course. But it's good enough as a model. Yeah, and then from the bulk crust is stratified. The lower crust is different from the upper crust. What is the reason? Why is there a different lower crust and a different upper crust? Any idea?
Container.
Composition is, but what is the reason?
There has been some differentiation.
Of course, but what by which can you make it more concrete? How does it work?
I believe there was perhaps lack of reasoning by underplating and other processes that melt the lower crust and also increases the plastic and
okay, I understand you are aiming at, but you can make it simpler. There is granite magnetism. That's all. This is what you say, this underplating, melting. Yeah, granite magnetism means melting of the lower crust, and the melt goes into the upper crust. And this produces a chemical stratification with time. It's very simple. Okay, so you end up in the upper crust, you have a little bit more tin than in the lower crust. And the same applies to tantalum and to tungsten, because all three elements behave during melting of silicate systems, they behave as incompatible elements. Incompatible means they go into the partial melt. There are also compatible elements, like chromium, for instance. If you melt the continental crust, produce a granitic melt, then the residuum will be enriched in chromium. It's just the opposite. It's a perfectly, or not perfectly, it's a compatible element, chromium. Actually, I have put it here. Chromium is on the first line. Huh? You come from the primitive mantle to bulk crust, melting of the mantle. Huh? And then the bulk crust has a much less, 20 times less chromium, because chromium behavior is a compatible element of melting of the mantle. So this is why it's very nice to look at these data. Just from the tables you can learn a lot. Try to understand what are the processes behind this pattern. Okay. Yeah, now again a little bit about the economics. Last year there was about 300,000 tons of tin produced by mining. And the biggest producer is China. It's nearly 70,000 tons of tin produced. And then comes Indonesia. Indonesia is 50,000 tons. These two countries have very different sources of the tin mining. Actually, China produces its tin mainly from primary hydrothermal tin deposits, but Indonesia produces all of its tin from placers around the Sunda Shelf area. There is no primary tin mining in Indonesia. It's all from recycled tin. It was the tin, the cassiterite which they are mining now is a heavy mineral in the alluvial and marine sediments. Originally, it was of course in hydrothermal deposits, which became weathered with time. If you should ever go to this area where they are mining, it's the Bangka and Belitung Islands of westernmost Indonesia. It's a flat landscape. It's a very old floodplain, a very old landscape where everything was eroded, deeply eroded, and the heavy minerals were preserved as placers. So I worked there for a while with the Geological Survey of Germany. It's a very interesting place. And what is interesting is that the primary mineralization is gone. You don't see it. You just see the placers. Sometimes you're lucky you see maybe the roots of some hydrothermal tin systems, but usually you don't see anything. It's the same in Malaysia, actually. I should mention here Malaysia. Malaysia is up here. It's very minor tin production. Actually, Malaysia was, 60 years ago, it was the biggest tin producing country in the world. Malaysia. Especially in an area with the name of the Kinta Valley, around the town of Ipoh. There's lots of Chinese miners there. And they did the tin mining. And also in the Kinta Valley, they were mining only the alluvial heavy mineral enrichment, only the placers in Malaysia at that time. Nowadays, Malaysia became richer, more developed, and they didn't want to have these dredging machines which destroy the landscape. This is why there is no more mining done. They have other methods to make some money. There are now golf courts and such things. Because this placer mining on land uses up a lot of land surface. In Indonesia it's different. They do the placer mining in the sea. They have deep dredges which can go down 50 meters and take up the sediment. But the placers in Indonesia, they are also alluvial placers. They are not marine placers, as many people may think. They are alluvial placers which formed about 10,000 years ago, and over the last 10,000 years, the water level of the oceans was increased by maybe 100 meters. This is why now the placers are mined in the sea, but they are originally fluvial placers. It's quite funny. Okay, so Malaysia today has no role. Huh? It's gone. But it was, historically, it's one of the biggest tin mining countries in the world. Yeah, and then comes Burma or Myanmar. It's becoming quite important now as a tin mining country. 20 years ago it was very low, but there it's especially under the influence of the Chinese people. People coming from China and they know how to do the mining. Yeah, and then we have Peru. And Peru is just one deposit, as you know, San Rafael. But it's a big one. A big, quite significant chunk. And then comes Brazil. Brazil has several smaller tin deposits. Then comes Congo, Kinshasa. Actually, this is the pegmatites, which we will talk about these later in Central Africa. And then comes finally Bolivia with 21,000 tons. Actually, Bolivia should have a much stronger tin production because there is much more potential than in southernmost Peru. For some reason, this is mostly political reasons, people don't want to invest. And then the production is low. Then we have Australia, Nigeria, and so on. Doesn't matter, but you should know the main countries are China. We have many hard rock tin deposits, usually is low grade, but in China everybody, any miner works at relatively low grade. Indonesia and Myanmar, Burma, and Peru. And actually the reserves are, the currently defined reserves are about 4 million tons compared to 300,000 tons, which means quite a not a big reserve base. This corresponds just to 10 or 12 years. But on the other hand, people can do exploration if they wish. If you don't do exploration, of course, then you use the reserves, and then someday there is nothing more left. Actually, tin has a very simple mineralogy with respect to economic aspects. It's only in one mineral with the name of cassiterite. Cassiterite is quite a heavy mineral. It's 7 grams per cubic centimeters. This is why it can be enriched in places. And it is more or less insoluble and mechanically stable. This is different from wolframite, for instance. We have lots of tin placers, but tungsten placers are rare or don't exist because tungsten, which is in the form of wolframite, is also a heavy mineral, but the wolframite easily breaks, it's brittle, and then dissolves. So this is why placers for tungsten are nearly. Yeah, now if we look at tungsten, then the different. China is in a very strong position. It's like the various elements before. So they dominate the market. And after China comes Vietnam, this is relatively new, and then comes Russia, North Korea. Bolivia very low actually. Bolivia also should have much stronger tungsten production. And the global reserves, they are at 4.4 million tons of tungsten, compared with about 80,000 tons of tungsten yearly production. So here the situation is different. We have for the next 50 years there is enough reserves. This is why prices for tungsten will not increase significantly. But for tin it can increase more, because the reserve base is so small. And then it comes to tantalum. Yeah, tantalum is part of the family with tin and tungsten, but it is restricted to one environment. This one environment are rare metal pegmatites, not hydrothermal systems, because tantalum is insoluble in hot water. So you can enrich tantalum by magmatic processes, but not by hydrothermal processes. In fact, you can't move tantalum by hot water. It doesn't dissolve. So there are no hydrothermal tantalum deposits. That's the consequence. There are only igneous tantalum deposits. Understand? All is logic. Yeah. Okay, so tantalum is always related to pegmatites, which also have tin and tungsten. And there the situation is like this. Congo, so-called Democratic Republic of Congo, is the most important producing country. I will give some pictures later from this part of the world, because I also work there. This is in Central Africa. And then Nigeria, in Western Africa, it just came out over the last years. It's just because the price of tantalum went up, and this is all artisanal mining. Actually, tantalum is produced in large part by artisanal mining, which means there are people from time to time they take a shovel or whatever, or penning, do some penning. Then comes Rwanda, quite significant. Also, Rwanda is a very small country. Then comes Brazil, China, Mozambique, and that's it. And actually, there is a huge amount of research. More than 400,000 tons of tantalum are identified as reserves, compared to the yearly production of only 2,300 tons of tantalum. But this production will probably go up, because tantalum is a very interesting element for the electronic industry and also for rockets and materials which must be very refractory, which must be stable at high temperature. Yeah, this is a picture which you can see in Central Africa. There's a boy, he has a shovel, and he moves the shovel in a smart way that he can enrich heavy minerals. So if you are not accustomed to this, you will not be able to do it. But this time we can learn it. It's just with a shovel. And then he picks out the crystals and puts them here in this plastic thing. And then at the end of the day, maybe he has gone for $1 or $2. Better than nothing. And this is the way how much of this tantalum mining, but also together with tin, is done. So what here is mining, I wrote here alluvial columbite cassiterite mining. Columbite is the tantalum, the essential tantalum mineral. And you see all these blocks of rock, white rock. If you see white rock, usually means igneous rock. It's either a carbonatite or it's a silicate rock. It's a highly evolved granitic rock. In this case, it's a pegmatite. So there is hard rock mining and pegmatite, and then the locals there, they try to get some metals out from the tailings. Now this is how the columbite looks. This is about 1 centimeter. Relatively coarse-grained material, black, and it's from the pegmatites. Yeah, columbite, I have here put the formula. It's high density. This is why it behaves like a heavy mineral. It's enriched in the places. It's chemically inert. Very high melting point, near 3,000 degrees. By the way, these columbite crystals, they are often intergold, or they have inclusions of cassiterite, which makes sense because tin and tungsten and tantalum go together. But they also have uraninite inclusions. I was very astonished when I saw this the first time. In fact, these rare metal pegmatites, they are also enriched in uranium, but the uranium usually is leached out by hydrothermal or other processes, and you see it only as inclusions in cassiterite or in columbite. Okay, that's the formula of wolframite, which you know. And there are some heavy minerals related to these wolframite and cassiterite are ilmenite. Usually it's ilmenite, FeTO3, rutile, TiO2, and tourmaline. Tourmaline is especially, as you know, in Bolivia, is extremely common. It's really astonishing. Yeah, so all over the world you see people doing this very small scale mining. And what they are penning here is white. This is the pegmatite. So they are penning the weathered pegmatite. This happens here in India first. And this is here in Burundi, northern Burundi. We call this ground sluicing. So the people, they collect and direct some water, rainwater, and then they make these channels, and then they move the rocks and all the material, move it a little, and on movement of the water, they can pick out the heavy minerals. So the heavy minerals are left behind. The other material is in suspended way, is transported. And here the white color, very everywhere in the world. It can also look like this. So you have here the plastic pipes. This is to channel your water, and then you may have a water jet if you wish, and shoot the water stream against this soft rock, which is weathered, and that's the pegmatite in this white material. Here this is in Rwanda, it's the pegmatite, which was mined by the Belgians already a while ago. Or it may look like this. This is a small pegmatite here. And they were mining this, and during mining then this developed this large structure, large feature. That's the pegmatite which runs out. In these reddish sediments, these are shales and sandstones. This is from Rwanda, this picture. Yeah, so we go back to the Central Africa. I showed you a similar picture before when we talked about rare earth elements. This is a small rare earth element deposit where I worked in Burundi for some years. And this is the Tanganyika Rift, or the Western Rift. And this province here, it goes down here to the south to Manono, all this province is called the Central African Metal Province. So it covers mainly Congo, the largest part is in Congo, but there's also Rwanda here, and Burundi here, northern Burundi. And there you have granitic magmatism at about 1 billion years, so 1,000 million year old granites. Related to these granites are pegmatites, same age, 1,000 million years. And these points here in red, according to their size, indicate the important metal deposits, which always have tin, tungsten, and tantalum together. Often the tungsten is out of the pegmatite that is in the rain system, because tungsten can behave quite mobile in hot water. And then the tungsten can be 1 or 2 kilometers away from the pegmatite in form of hydrothermal rains. But tantalum always remains in the pegmatite because it's insoluble in water. Now, by the way, this deposit here is Manono. Famous place is the biggest pegmatite deposit in the world. Biggest metal pegmatite deposit in the world. I will show you some pictures of this stage. Yeah, this typical landscape you see here, this is the pegmatite. And the locals, usually this means the farmers, they did some simple mining here, and this is why it's outcropping. And then here these are the tailings, here is the river valley. So from the distance you see already these pegmatites, even if they are small. Because the locals try to make some money to pick out the columbite crystals or maybe test it out. That's a geological map of Rwanda. Here's a lake, Lake Kivu. And you see the red, here the same is this granite magmatism of various ages. You didn't distinguish this. But the granite magmatism with 1 billion year age is related to pegmatites, and this is this red lens-like features here. So there are usually pegmatites formed not alone, they form in fields, pegmatite districts. So there may be hundreds or even more small and large pegmatites. Now this, for instance, is relatively small. Here's an animal, and you see this is the form of the pegmatite. Actually, the pegmatite forms wherever there is some permeability, just a space problem. And here you see this is probably some related to some tectonic features. Well, this is a very small pegmatite, very nice, maybe just 1.5 meter thick. And given the tropical climate, we have quite weathered rocks. Most rock is a shale or a sandstone. And people then can easily mine this pegmatite just as I don't know, this is my hand. So they have their own materials to get the columbite and cassiterite. If the rock is fresh, then it may look like this. You have coarse-grained quartz, and the reddish material is K-feldspar. Then there should also be some albite here. This is probably the whitish material. This is probably albite. This is a normal pegmatite, just a coarse-grained granite. It's the same. And this material, these pegmatites are related to highly evolved granites, which are exposed in this case here just a few kilometers away. This is an interesting granite texture. It is coarse-grained to fine-grained to medium-grained, then very fine-grained. We would call this an applied. So it's an applied pegmatite granite system. In fact, it doesn't make sense to much distinguish applied pegmatite and granite. It's all chemically it's the same situation. Yeah, this is columbite under the microscope in the polished section. This is 1 millimeter. Columbite, and then often columbite has cassiterite inclusions, which form at very high temperature. This is an oil with which activity of cassiterite becomes formed. Yeah, and then a short picture here from Manono. This is probably the biggest hard rock rare metal deposit in the world. 400 million tons. And nowadays, actually, what people are interested in these pegmatites is the lithium. So I could have, as a title of my talk, I could also have added lithium, because this all goes together. We have enrichment of tin, of tantalum especially, then lithium, but together with lithium there's also cesium and rubidium enrichment. So it's quite a big family of lithophile incompatible elements which are enriched here. But you see the enrichment is 1.65% Le2O, and it has tin, 700 grams per tin, which is good, and a little bit tantalum. And in the tailings, this is from the times when the Belgians did the mining here. In the tailings, there's still a quite good lithium and very interesting tin and tantalum. So this is a pegmatite here. The pegmatite runs like this. It's more than 10 kilometers. These are the old tailings from the Belgian colonial times. Currently they are mining these tailings because there is a dispute about the ownership of this pegmatite between various companies. And the lakes developed because there were some open pits in the Belgian times. Yeah, as Manono has actually the lithium, this is what people are interested in today. Lithium is in spodumene and in lepidolite. Lepidolite is a mica, but spodumene is a real lithium mineral. So the more spodumene you have in a pegmatite, the better it is to process and easier to more economic it is. like here, this is the spodumene is this mineral here, this greenish material, and the lepidolite, the mica, has this rosé color. This is 5 centimeters. And this is the whole Manono pegmatite. It's not a continuous pegmatite. Actually, it's several smaller pegmatite bodies, but usually call it just the Manono pegmatite. Because in between here, this color is meta-sedimentary rocks, meta-protozoic rocks. And the age of Manono is also around 1 billion years. Yeah, if you look, so let me just say a few words about lithium, because this is also quite popular, and it's part of what we are talking here about rare metal granites. So one of the biggest, or maybe the biggest one is Manono here. That's the grade in terms of lithium between 1.5 and 2%, and here's the tonnage, very big. And second place is Greenbushes. Greenbushes is in Western Australia. This is an Archean pegmatite, very old. Nobody really knows how this formed because there's apparently no granite exposed. Anyway, Greenbushes has a little bit less lithium, and tonnage is a little bit less, but it's in Australia, which makes life easier than in Congo. And then comes this is also in Western Australia here, and then comes some other deposits, which I will not go into any detail. Yeah, this is Greenbushes. Greenbushes is quite a big pegmatite also. Again, you see the white color. And Greenbushes has, well, an interesting tonnage, very good lithium content, plus interesting tantalum and tin content. And the lithium is in spodumene. This is a good thing because there are other deposits, lithium deposits, where the lithium is mainly in mica. And if the lithium is in mica, such as in lepidolite, for instance, then you need much more complicated processing of the material. So it's a big advantage if a pegmatite has spodumene. Actually, there are other deposits with lithium. These are Geisen deposits, directly related to granite. In the uppermost part of the granite, hydrothermal alteration. These Geisen deposits can also be very big, and they can also have an interesting grade. But there, the lithium is all in lithium mica. And to extract the lithium from mica is quite costly. It requires a lot of energy and machines. So spodumene is what people go when they look for hard rock lithium deposits. Yeah, now the geochemical evolution of pegmatites was studied a long time ago, 50 years ago. This is, for instance, from 1989. It's nothing new. But if you pick out individual minerals from a pegmatite, like feldspar or mica, then you see in between the different pegmatites, you see a chemical evolution. You can do this, for instance, here is cesium plotted. ppm, this is cesium on the x-axis. On the y-axis, you can put potassium divided by rubidium. Actually, this is quite stupid. These people apparently like to use this ratio because in K-feldspar, potassium is a constant number. The potassium content of K-feldspar is defined by stoichiometry. So you could, to make things easier, just put rubidium. Inside, some people think it looks better if we use some more complicated things. Here they should have just, but anyway, what you see here, there's a chemical evolution from less evolved. This could also read 1 divided by rubidium. So in fact, if they would have put here rubidium, then the picture would like this. This would more to my taste. So we can say from these evolved phases of pegmatite, these evolved phases have low cesium and low rubidium. And this chemical evolution rubidium and cesium increase by orders of magnitude. This is again a logarithmic scale, 1, 2, 3, nearly 1,000 times. Chemical evolution, fractional crystallization, we call this. Because you see this is a linear correlation between rubidium and cesium. This linear correlation indicates a process which we call fractional crystallization. I don't know if you have heard about Rayleigh fractionation or so. There is a Rayleigh law. If you have this kind of distribution in log space, linear distribution, which this means Rayleigh type fractionation. So this is the most fractionated pegmatites. These have metals, that's for sure. One is, for instance, tanko. Tanko is a classic metal pegmatite in Canada, in Superior province, which was studied already 50 years ago. And this is very highly evolved metal pegmatite. You can also do this looking for tantalum, for instance, on this side, and cesium here. Then you see the same situation. You go from low cesium, low tantalum. This is, for instance, low calcium granites. This is already relatively evolved granites. And from there, goes up here by orders of magnitude when we end again in tanko or some other pegmatites. It's enormous. This is by orders of magnitude, some incompatible elements are enriched. Lithium is the same. We don't have a picture here for lithium, but lithium also, this fractionation increases its concentration. Yeah, so this work on pegmatites was already here in the 1960s, 1970s. These are two Russian people. They studied this in Russia. And they defined a threshold which can be used in exploration by analyzing muscovite. So if a muscovite has at least 20 ppm tantalum, then you can expect a tantalum deposit. This is what this guy thought. The other guy suggested something like 65 to 70 ppm. Doesn't matter. Anyway, if you have a strong, if you see in the muscovite a strong tantalum concentration, this means you are in a tantalum deposit or close. And then there's another thing. There is zoning at a kilometer scale. This is an example from, it's also from the Superior province in Canada. So this is a granite, which has the same age as the pegmatites here, so it's probably the source. And then you see here over several kilometers. This is a scale, 1 kilometer. 1, 2, 3, 4, 5, 6. About across 6 kilometers, you see different lenses. Pegmatite, with, in this case, they analyzed potassium, rubidium, and K feldspar. And the lower the ratio, the more rubidium is in the K feldspar. So you see that the rubidium content increases here. These are low rubidium values because they use potassium rubidium ratio. It's stupid. They should have got the rubidium, but they prefer this. So you see here a chemical evolution. These are the most evolved pegmatites up here. And this is Bierslake. Actually, tanko is more or less here. This is probably tanko pegmatite. Yeah, and then you often see in the textbooks, which is from the Geological Survey of Canada, a very nice book, Geology of Canadian Mineral Deposit Types. You can learn a lot. But the picture here is not really good, because this shows pegmatites related to a granite source. And the more you move out from the granite source, the more the pegmatite becomes enriched in lithium, cesium, beryllium, tantalum, niobium. And if you go more inside, then it's barren. So there is a chemical evolution. But what is missing is this kind of picture. There is, of course, it's impossible to have these lenses isolated in the rocks. There is connection. All these lenses must be connected here with deeper parts of the brain. This usually is, I don't know why people just don't see the fractures maybe. Because these pegmatite melts, they have a very low viscosity. They have lots of volatile components which depress the viscosity. The pegmatite melt behaves like water. So if there is just a fracture, then the pegmatite melt will move along this fracture and you don't see much, maybe not even traces, and it will only crystallize where there is some space. This is why people often use this kind of cartoons where the pegmatites look as if they are isolated from each other. This doesn't make sense. So this is already better. Actually, this is from Germany. Actually, this is a specialist of pegmatites. Anyway, at least he put some structures here. But some of the pegmatites in this case also are isolated. I don't understand this way. Anyway, the main point is the further you go out, the longer the way of crystallization is, the more evolved these pegmatites are, and the most tantalum-rich pegmatites, also lithium and tin, which they are in the outermost part of this zoning sequence. This is a very important thing which you must not do. Should ever work on such a systems. This is just the basic model, but I think this is quite good. Yeah, this makes now more sense to me. This is a model from Möller and Berlin. Actually, we have a granite here, and then fluids from the internal part of the granite, from the residual fluids from the granite. This crystallizes first because it's a cold wall rock here. In the inner part, you have the residual melt, which moves along fractures. And if there is space, this here, if there is a little bit tectonism involved, then you open up spaces. This looks like a full apart basin. And then you have the pegmatite can crystallize. Yeah. So this looks to me like a reasonable model. Actually, we also have proposed a model which is more or less the same. We have a granite here, then in the granite, we often have barren pegmatite or Breisenization. Breisenization is just the magnetic fluids from the granite which heavily alter, pervasively alter the rock. The Breisen is just a quartz mica rock, the porphyry. And then going further out, we come to the tantalum tin lithium deposits further out. And what we also observed in Central Africa, there are usually, quite often, veins, quartz veins with gold and bismuth. So we think there is a connection between these rare metals and gold as well. Because the gold can also be represents the stage of evolution of the granite system. If you think about copper porphyries, for instance, there are some copper gold porphyries, or even only gold porphyries, where the gold is the result of the magnetic evolution by the hydrothermal oscillation. Yeah, so we have here these small pegmatites, and well, it's good. So now I will focus in the following on tin, because this is a nice example to do a little bit more in-depth research. Now I just showed you a few basic features, but with tin I'm more involved in research, so I will show you a little bit more. But first, a general picture. So in this map, I summarized the historic tin production for the last 2,000 years. This was published in 1990. So in fact, up to 1986, there was a cumulative historic tin production of, let's say, 18 million tons of tin in the world. And this cumulative tin production came from a few parts of the world only, especially here from Southeast Asia. Indonesia, Malaysia, Burma, Thailand, and a little bit here in South China. So historically, This is the most important tin province in the world. Because you see that the tin deposits, they form provinces. They are not all across the map. They are related to certain small parts. This is what we call a province. So this is Southeast Asian tin province. This is common. But we also have Cornwall. Cornwall is, nowadays there is no tin mining, but they had important tin mining since Roman times, since 2000 years. In the Middle Ages, this was quite an important tin mining area. Then there's a little bit, this is in Germany, and Czech Republic, Spain, Portugal. Okay. And then comes Bolivia. Bolivia is also not unimportant. Bolivia is also an important, at a world scale, an important tin province. Then there are a few others. So I did then, a few years later, I did this. This was in 2018. I updated these historic numbers with the production up to 2018, and nothing changed. The additional data is the red rims here. So we remain with the same tin provinces. There's no new tin province found. Same tin provinces, and more or less the same situation as we had 20 or 30 years ago, no, 40 years ago. Yeah, then until 2016 it was already 25 million tons of tin which was produced cumulative, historical, over 2000 years ago. Yeah, now I show you first a few pictures. This is from the old times, when there was still tin mining in Malaysia. This is in the Kinta Valley. It's a beautiful mine. And what they did, they mined this by monitoring, they call it. They produce a water jet. This is water pipes here, metal water pipes. This is this produces a water jet, it's a water cannon, and they shoot with the water at the rock here. It's a hard rock. But the water jet is quite strong, and it breaks the rock, and then the fragments flow down here, and they are put on, when they are processed. Yeah, this was I think I put this picture in 1985 or so. At that time there was still a lot of mining in Malaysia. And actually what they're shooting at is this surface of a granite. It's a smooth surface due to this jet material, because it's a water jet. But what you see here is what we call a sheeted vein system. Sheeted, because many veins parallel to each other. And the whole thing is a granite, but it's a heavily altered granite. And in this part here, similar to Bolivia, there's also tourmaline, a very important component. Tourmaline means there is boron metasomatism. This means the fluids were rich in boron. They went migrated through the rock and produced tourmaline crystallization. And tourmaline is also on these veinlets, together with quartz and cassiterite. And then they put this fine material, they put this here on these inclined wooden channels. We call this process fusing. And then the heavy minerals are retained at these rivers. So it's a very simple. The Chinese are masters of this. There's the Chinese flag, but it's in Malaysia. The Chinese are masters of this kind of relatively simple mine, without too much technology. Yeah, and then if we go south, in the Southeast Asian tin belt, then we are in Indonesia. And this is a tin dredge. So here we have the Sunda Shelf. This is a shallow water, 40, 50 meter deep, or more, but for hundreds of kilometers. And there are these alluvial placers which are now drowned because of the water level rise over the last 10,000 years. Now, 10,000 years ago, there were the ice ages. So there was lots of water in the ice, and when the ice was melting, then the ocean level went up quite significantly. Not like nowadays, actually, the glaciers are melting and the ocean level is going up. So there's a big dredge, and this dredge goes deep into the water and takes it from the bottom, takes the sediments, and it's processed directly on the dredge. It's like a factory. Yeah, and then comes another aspect. Often, usually people distinguish between tin and tungsten deposits. So they think it's correct, there are tin and there are tungsten deposits, but people think that these are different systems. This is not, must be different processes behind this, which I do not share this idea. And I just show you a picture of large-scale metal zonation. This is from the mole granite in New England in Australia. So this is the intrusion here, and there is a tin and tungsten deposits, and you see that there is a zoning, especially lead, zinc, copper, is in the outer parts of the system. And this is typical, you can observe this everywhere in the world. Lead and zinc are the most mobile components in all hot water, and this is why they are usually separated in space, but not in time, but in space from those parts of the system which are of higher temperature. So this is the high temperature part of the system, and there is certain parts where it's tin dominant, and other parts where it is tungsten dominant. This is the same granite situation. In fact, the reason why there is so much tungsten here, this is a sediment which is left here. That's the intrusion. And this is a remnant of the host rock. And the host rock here has calcium and iron, and then the solutions which are rich in tin and tungsten, and they will precipitate wolframite or scheelite, but not cassiterite, because the solubility and behavior on precipitation of tin minerals and tungsten minerals are completely different, and I will explain this to you later. Yeah, this is actually, there is a term tin granite. And this term tin granite was already coined by a person with the name of de Beaumont. Actually, he was the chief of the French Geological Survey in the 19th century. So he observed something, that there are two different granites. One type of granite is primitive, as he called it, the other is a tin granite. And he observed that the tin granites have some special features. He called them the monstruosité de granite. Monstrous. They are somehow unusual. There's a character ultragranitic, which means a lot of quartz. And then he observes that these tin granites are often sub-intrusions which reach out of larger granite massives. So these are basic observations which he wrote already in 1847. And this means, actually this is what we call today, we have multiple intrusion sequences. So a granite is never just one intrusion. This doesn't exist. There are maps where you just see a red area, and you think this is one intrusion. No, it doesn't exist. All granite intrusions are multiple granite intrusions. They consist of different intrusive phases. Even if you don't see it macroscopically, there are different phases for sure. If you go in detail, you can find them. So we always have multiple intrusion sequences, which means this is the reason that the latest intrusive phases and also the smallest melt fractions are the most chemically evolved. So you have more or less, let's say, you have a big reservoir with partial melting in the lower crust or middle crust. And from this reservoir, small parts are moving upwards and building up a batholith or plutonium. And the latest phases, they are most evolved, and they are also at the same time the smallest in volume. And sometimes they are not even outcropping. Like in Bolivia, you don't see these highly evolved phases, but they are there. At least I am sure. And everybody must be sure. I think because these intrusive sequences consist of many evolutionary steps. And in addition, actually, what we have in Bolivia, we have these big caldera-type structures. And below these caldera-type structures, we have zoned magma chambers. And these zoned magma chambers can go from not much evolved, like bayside or less, up to high Neolithic. And the tin is related to the Neolithic phase, which we often do not see because tin goes easily into the hydrothermal fluid and then moves out of the system, maybe for 2 or 3 kilometers. But I come back to this later. Now this picture also shows the different styles of tin mineralization. We just talked about applied and pegmatite, but here we have an intrusion. This Greisen is this quartz muscovite alteration, late stage microgranite, usually in a fine grain, highly worked white material. And then the tin usually is in vein systems, which can be quite large. If you have put a big scale here, this is 500 meters. So these are the vein systems, or the tin can be in skarns. If there is some carbonate rocks, sedimentary rocks, then it can be in skarns, or we call this carbonate replacement a little bit outside, where we don't see skarn minerals, but we see that the carbonate minerals have been replaced by including cassiterite. And the alteration halo is quite large here. Around these veins, there is always hydrothermal alteration. An example of such a multiple intrusion sequence, a classic example is here, was published by Yin. So we have here already, this is already an evolved granite. It's a protolithionite muscovite granite. So this is already a highly evolved granite. And then there come some smaller phases intruding this, up to some phases which are then to pass lepidolite granite. This is one. So this is where lithium is extremely enriched, but also the cassiterite and tantalum. So what I wanted to say is you have an intrusion sequence from larger volumes to smaller volumes. And this is just a consequence because we have a larger volume, intrusive volume. When this crystallizes from the margins, then the residual melt develops chemically. It must develop. So from time to time, residual melt can escape the larger magma chamber, and the later this phase is, the more evolved. Yeah, this relates here to what we had in the morning. The incompatibility of an element relates to ionic radius and valency with respect to the major components in a rock. The major components are magnesium, iron, aluminum, silica. So these are the major components. And then further out from this field, with respect to valency and to ionic radius, are those elements which we call incompatible. Those elements which are close to the major components, they behave compatible. Close, in terms of valency and ionic radius, they are compatible. But if they are further out, they are incompatible. And here we are talking about tantalum and tungsten. They are incompatible. And tin, for tin, I have put here 2 points. Because tin exists in the 4+ state, where it is close to titanium. And if tin is in the 4+ state, in a melt, then it cannot behave incompatible on crystallization. It will crystallize together with titanium minerals. It will be part of the biotite, for instance, which means that the tin 4+ is not able to be enriched in the magnetic system. However, if the tin is in the 2+ state, then you see it is clearly out of this inner part here, then tin can behave incompatible. So this behavior of compatible, incompatible depends on valency, on ionic radius, but also on the redox state, on the oxidation state. Tin 4+ is the oxic form of tin. And tin 2+ is the reduced form of tin. Now the question is, how relevant is this now for nature, for granites? But I will come back to this later. Here is the Beauvoir granite. Is a beautiful, highly evolved granite. You see white. Actually, it was a China clay pit, and now they are transforming this as a lithium mine, because it has an interesting lithium resource, but the lithium is in mica, so it will be expensive, this mine. But this mine also has tin and tantalum as it should be. And I just want to focus here on this white color, which looks really nice. The Beauvoir is in the Massif Central in France. It's a Brazilian granite. Well, this is another beautiful example. This is in Siberia. It's the Orlovka metal granite. You see these big blocks here. This is a Amazonite granite, highly evolved granite. The solidifications, unidirectional solidification structures. You see the feldspar crystals here. They are aligned perpendicular here to something which crystallized before. And Amazonite, this is the same as K-feldspar, is greenish actually. This is the Amazonite. So this is a K-feldspar crystals. This was the most important tantalum deposit in the former Soviet Union. Yeah, well, just coming back to this Greisen versus pegmatite situation, coming back to the lithium. So the lithium mica Greisen deposits, they develop in the upper parts of intrusions. They can be big. Usually the grade is not so big, but the main point is the lithium here is in mica, while here the lithium pegmatites like green bushes and monono, the lithium is in spodumene. Yeah, now I'll just jump it here. But now I have to show you. Actually, this is in the Himalayas. The Chinese part of the Himalayas. Himalayas, many people thought there is some granite, but people thought there is no tin. Doesn't make sense. But there is actually a Chinese part. So this is a dome, a metamorphic dome with a number of granite intrusions. The scale is this is 2 kilometers. So it's a dome, let's say 20 to 40 kilometers, with several igneous intrusions. And in this part, they discovered tin mineralization in various modes of mineralization. I'll show this later. Yeah, this is this part. And actually, this is a dome. A dome, a granite dome. This is the least evolved granite here, and then comes the most evolved granite up here. And they did quite detailed dating of all these rocks, and the zircon ages range from 40 to, let's say, 15 million years. So we have here a granite sequence which covers something like 25 million years. I remember in the old days, people thought, well, we have a granite intrusion here, we find an age of 50 million years, and we find an ore deposit here which is 60 million years. This doesn't go together. But you must know that these granite intrusions always consist of various parts and of various ages, because the formation of a granite intrusion requires heating in the lower crust. In the end, it's the mantle which provides the heat. And this is a process which goes very slowly. So you have to calculate in tens of millions of years, not just in 1 million years, which means the lower crust is slowly heated up and then it produces melts. So it's a very large range. This has been found in other parts of the world as well. If you analyze in detail these batholithic granite intrusions, you find a large spread in ages. People before they thought, oh, maybe these ages are wrong. Maybe the system was disturbed. No, it is just the time evolution of granite magnetism. Same, by the way, for copper porphyry systems. There is Las Bambas here, not in Peru, the Jurassic system, and there they have ages from 30 to 10 million years, granitic phases. Usually, the tin, but also copper mineralization is related to the youngest phase, which is the most evolved phase. This is, they did cassiterite dating and columbite dating. Because cassiterite and columbite have a little bit uranium, not too much. Therefore, it can be dated. And the dates are usually corresponding to the youngest granitic phase. This is also something which you can observe in many parts of the world. Ah, yeah, this is the same system which I just show to show the different modes of occurrence of mineralization. We have some, for instance, here we have stratiform. Comes the latest phase, fine grain, like acritic. So we distinguish three main phases, and this is the latest phase, the microgranite, because it's fine grain. And the microgranite is what is related to the hydrothermal mineralization. Actually, this is an example here. Here you show you these two-phase granite textures. Here we have, this is quartz. These are thin sections. This is quartz, this is K-feldspar, and this is plagioclase, this is K-feldspar. So we have big quartz and K-feldspar crystals set in a fine-grained matrix. Here is the same. This looks like a plagioclase. This is K-feldspar. This is also K-feldspar here, in a fine-grained matrix. So there is in between the coarse-grained material and the fine-grained, there is a break. And we connect this break to the exsolution of an aqueous fluid phase due to sudden pressure release. Sudden pressure release and fluid exsolution. You know, if you exsolve a fluid phase, then the volume must increase, because the volume of a water-saturated silicate melt is smaller than a water-saturated silicate melt plus the exsolved aqueous fluid phase. Volume, it means expansion. Expansion means mechanical energy. This means breaking. Brachiation. Okay. So, and we see this also, such textures we see, for instance, in San Rafael in Peru. You know, that's a really big system. Very interesting, it's high grade. It's also a near surface high grade copper, not only tin. And this is the megacrystic granite in the mine, underground, 24 million years. And then here's again, then you have fine grained material going in here, so acritic. It's the same age. So here you have again the megacrystic granite, and you have a medium grained granite, and you have fine grained granite. Then you have, this is also interesting, a lampo fire, which is cutting through the granite. And sometimes you even see that there are xenocrystic or xenomaterials of lampo fire or other mafic rocks swimming in the granitic rock. You see this here? It's very interesting. These how do we call this? Do you have the right name, maybe? Do you happen to know the right name? What would you call such things which are xenonids? Yeah, let's say xenonids. Huh? So yeah, this is what I wanted to say. We have mafic xenonids in felsic melt. This is what we see. So this means there is some connection. And this relates to the big picture that granites do not form just near the surface or where you see them now. They form at a deeper level where the mantle also has some influence. Yeah, then another big feature, the microgranite can look like this. This is 5 millimeter here. This is Polish thin section on the frost nipples. So these highly evolved faces, they consist of muscovite alkali feldspar microgranite. In this case, there's also garnet, by the way. Garnet, if you find garnet in such a granite, this means the granite is per-aluminous, because otherwise garnet cannot form. Garnet takes up a lot of aluminum, but no alkalis like feldspars. So if there is an aluminum, an alkali deficiency, then you can produce garnet. And this immediately tells you this is a per-aluminous granite. You can also do it by chemical analysis and so on, but you can also see it in the field. Actually, some other features here. In German, we call this a Schnittmustergreisen. This is from Altenberg in the Erzgebirge. So this is the granite, the fine-grained granite, and we see here these are fractures which are filled by, in this case, by lithium mica. In the Erzgebirge in Germany, they don't have so much tourmaline, but by experience, if there is no tourmaline, then you will have lithium mica. I don't know why, but it's just an observation. Yeah, if we go to Cornwall, this is a famous place here, Cornwall. So this is a scale, and this is the first. So this is a cliff, maybe 100 meter high. And you see here these holes. This is from medieval tin mining, and they were mining. You see these structures. It is a sheeted vein system. Yeah, Cornwall produced quite significant amount of tin, but about the equal amount of copper also from the same systems. So copper is not that rare in tin systems. Yeah, this is Klinger Head here up here. Klinger Head, this is on top. This is under protection. This is a national monument in England. And here you see again this sheeted vein system, and it's all greisenized. You still see this is a K-feldspar megacrystal granite, apparently, with the white material, but this material is pervasively altered. I don't know what. I mean, first you would have a sericitic alteration, but maybe there's also this artilic alteration. I don't know. But what you see is a sheeted vein system with these structures here filled by lithium mica. So this is Cerro Chacaltaya, 5,400 meters. There's a road running up here, so you don't have to climb. You can just go to a parking lot here, just below. Very nice place. I always go here with my students the first day when we do the field trip in Bolivia and Chile. And along this road here, and this is the essential point, about here, there is a small granite porphyry intrusion. It got really small. And even difficult to detect because this granite porphyry intrusion is in large part greisenized. And the greisenization, which means high temperature alteration, destroys not only the minerals but also destroys the texture of the rock. So it's difficult for some of these rocks. It's difficult to tell what was this rock originally. It's a greisenized granite porphyry, and related to this small intrusion here, really small, there is a hydrothermal system which runs like this. 15 kilometers. It's amazing. And the other amazing thing is here in the background, these are all granites. So it's a Cordillera Real. Why not put the sea would be here? So these are mostly granite intrusions. And I did some mapping here around these granite intrusions. You just see a small halo of thermal metamorphism, but no hydrothermal alteration. The hydrothermal alteration should be on top of an intrusion. And here, these intrusions are already weathered deeply, or eroded, I wanted to say, to a relatively deep level. While here we have a granite porphyry system just at the right situation, where we still have the hydrothermal system preserved. There's no reason to believe that there were no hydrothermal systems related to these granites, but they were here 1 or 2 kilometers in the air and now eroded. By the way, this is the Katari formation, this is Saluria. Yeah, this is another horizon picture, and this is a plain light under the microscope, it's in section. So here you see from Chakataya, here you see this is tourmaline. This is typical tourmaline, this is acicular shapes, and this is cassiterite crystals, rhomboedric cassiterite crystals. Yeah? And then there's also a little bit, this is apatite. And the matrix here is quartz, there is no feldspar. Because Reisenization means no feldspar. And so if people describe a rock and call them Reisen, when the rock still has feldspar, then there is something wrong. Reisen is completely feldspar destructive alteration. This is the same under cross-nickels. You see there's lots of quartz here. And this is the tourmaline, and this is the cassiterite. And then in the same area, you see strange features like pebble dikes. So these are dikes, like this, with some redondeados, the granito, this whitey stuff, argillic water, in the matrix of fine-grained matrix or tourmaline. So it's a hydrothermal vein, which was so energetically active that it transported rounded granite clasts along its way. So the system had enormous amounts of energy. You will notice from volcanoes, from other porphyry systems, and lots of tourmaline. All the dark stuff here, slightly bluish in this picture, is the tourmaline. The tourmaline is everywhere. Actually, this is also this from Cornwall now. Just going back, the black stuff is tourmaline. In fact, this relates to exsolution of boron-rich fluids, which breaks the rock. There's also broken granite, and all the dark material is tourmaline. Tourmaline fracture, we call this. And this is another piece from the Chakataya area. The Chakataya area consists mostly of Katari formation, which is a kind of a turbidite, quartz clay material. What you see here is a lode cast, sedimentary features, and you see here graded bedding. Actually, the upper part of the unit is fine grain, becomes coarser grain, and lighter in color. And the point is that all the dark material, this here, even here, more, is tourmaline, very fine grain tourmaline. So the boron metasomatism is able to preserve these fine sedimentary textures. Actually, the boron metasomatism acts most here, of course, on the clay-rich material. This is why it's dark here. There's more tourmaline than in the sandy material. Because tourmaline needs aluminum. And in the same area, we have these mantos, but the mantos consist of quartz units, 2 meter thick, which are broken, brecciated, and the brecciation during the time of mineralization is preserved in this paleopermeability pattern, preserved due to tourmalinization, which runs along the fractures. So this is the permeability pattern. So there were fluids running through the rock, producing these small tourmaline halos together with cassitoid. The modern day fracture system is completely different. There's nothing to do. Are you too tired now? Because it's still I'm now going back into chemistry a little bit more sophisticated. What are you trying? Of magnetic fractionation, titanium behaves as a compatible element during fractionation. And titanium is not much soluble in water. It is soluble, but not extremely. And it is a compatible element because it goes into mica and other titanium. Tantalum is different. It is incompatible. What's the right word? Yes, incompatible in English. Tantalum is incompatible and is not soluble in water. So this is good. If it's not soluble in water, then it may preserve the igneous situation. This is why I use these two elements. And I plot them in log-log scale here, because if the rocks should make a linear correlation in log-log scale, then I know I'm dealing with Rayleigh fractionation. This is another story. I could need another hour to explain this. Anyway, I have plotted here many data. This is from a large database. This is just felsic igneous rocks. It's more than 68% SiO2, and they are not too far from bulk plus. No? So that's the normal average granite repulsion. And then you see some granite sequences like this one. This is from the Erzgebirge. Erzgebirge has over 20 million years. Has a granite, younger and older granites, which was already mapped 100 years ago. But they couldn't date at that time. But now we know that these are the youngest intrusions. And in addition, they did very good mapping in the Erzgebirge already 100 years ago, so they distinguish the different granite faces. So these are all different granite faces, and each symbol represents several samples, several very large samples. Because during socialist times in Eastern Germany, they had enough money for exploration and science and so on, and they put enormous money in exploration for tin. And this is why they developed very interesting geochemical results. So this is the chemical evolution of the Erzgebirge granites. They have an age of, let's say, 325 to 305 million years. Okay. And then I have a few others. This is the border range from Thailand and Burma. These are individual samples which plot like this. And then I have data from Massif Central in France. This is largely from the Beauvoir granite, which I showed you, this white granite, highly evolved. These are the pegmatites in Rwanda as an average. We took many samples in Rwanda. And this is individual samples from a tantalum granite in the eastern desert of Egypt. This is the name of Abu Dhabi. It's very highly evolved. And you see that the whole thing aligns along the line, linearly correlated. Also, these are completely different places. But they align along this, here, like this. And this means they are related to fractional crystallization or Rayleigh type fractionation. So this is usually my first thing which I like to show people, because tantalum and titanium are close to the igneous situation. You don't lose these elements during hydrothermal alteration.